Okay, today we're going to learn about how to draw more advanced Lewis structures, including exceptions to the octet rule, ions, like for instance ionic compounds, and also structures that have resonance. So the first thing is, for the warm-up, draw the Lewis structure of CHCl, CH2. See if you can figure it out. This one's tricky. The key thing is you're going to need 4 bonds to each of your carbons. So for here, this carbon is probably bonded to an H, a Cl, and a C, so that's only 3, but that's probably the best you can do. And this C is probably bonded to its 2 H's and the Cl before it. So first, let's do our standard thing, which is count up our valence electrons, which is 18. And then we put all of our atoms around the centers. The carbons are going to have to be the centers. We connect in single bonds. We subtract our electrons. That gives us, because we put 5 single bonds in, subtract 10, that leaves us with 8. And now we add pairs of electrons trying to fill the octets. Remember, carbon has to have a full octet. So you can see that this one's got an octet, this one doesn't. So we're going to have to do something to fix that, and that is put in a carbon-carbon double bond. So this is a good Lewis structure for this compound. Okay, now, exceptions to the octet rule. Molecules made with boron and beryllium, these are small period 2 elements, those are really going to be the centers of these compounds, have less than a full octet when combined with fluorine or chlorine. So here are a couple of examples. Here's beryllium dichloride or boron trifluoride. And you can see that the beryllium dichloride has only 1, 2, 3, 4 electrons around the middle. Now this is an older drawing used for IB chemistry where they don't use lines, they use X's and dots for electrons. But this is 2 electrons in a bond to this chlorine, and this is 2 electrons in a bond to this chlorine. Same thing for boron. It can have a center with only 6 electrons around it and still be stable. So boron trifluoride does not have 8 electrons around the boron. So got to remember, beryllium and boron are exceptions. Now, some molecules also have expanded octets. So molecules that contain sulfurs and phosphorus in their center, there's other ones too, but these are kind of the standard ones, can violate the octet rule. They violate it by actually increasing the number of valence electrons around the center atom, which is going to be sulfur or phosphorus. So these are known as large period 3 element centers. So here is sulfur hexafluoride, SF6. Take a look at the sulfur in the center. 1, 2, 3, 4, 5. There's 6 bonds to it. That means there's 12 electrons, 12 valence electrons around the sulfur. Fluorine never violates the octet rule. Each of those has 8. Now, all of these molecules up here that I have listed have expanded octets with 10 or 12 electrons around the center atom. And remember, if you substitute another halogen for like the fluorines or chlorines, you're still going to get the same kind of structure. So PCl4F would be the same. F3Cl would be the same. SCl6 would be the same. They'd have the same Lewis structure because they all have the same number of electrons, and you're just swapping things that are in the same group. Now, some atoms never violate rules. I could mention this in some of the videos. Hydrogen will always have 2. It'll never violate that. So I guess that's the duet rule, so it never violates it. Carbon, nitrogen, oxygen, fluorine will never violate the octet rule. Never, ever. Okay? So they're always going to have 8 electrons around them in any molecule. So with that in mind, which of these structures is incorrect? Take a moment, write it down, figure it out. Okay, the structures that are incorrect are right here. Why? Well, it's supposed to have 18 total electrons. Everybody's got an octet, but add them up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Oops, I added a couple of electrons and didn't tell you. This is an octet exception. It's good. This is an octet exception. It's good. Here's carbon. Oops, 2, 4, 6, 8, 10. Carbon's got 10 electrons around it. Carbon never violates the octet rule, so C is definitely incorrect as well. Now, Lewis structures for ions are very easy. If you look at like binary ionic compounds, as an example, the metal ion is in brackets with no valence electrons around it, and we put the charge outside the bracket in the top right corner. Non-metals ion, we put it in brackets. It's got 4 pairs of valence electrons around it, all 8 valence electrons, and it also has brackets with that charge on the top left corner. So for instance, if we were going to draw the Lewis structure of magnesium sulfide, it would be magnesium with a 2+ charge in brackets, and then sulfur with the 8 valence electrons shown inside brackets with a 2- charge. Boom, done. So Lewis structures of ions are generally pretty easy for ionic compounds. And there's a couple of examples that I gave you in the other video. Now, structures of polyatomic ions can be more tricky. We still use the same rules, all right? They're ions, we're still gonna have brackets and the charge outside, all right? But we also have to think about what that charge means when we add up valence electrons. So when we add up valence electrons, if we've got a positive charge, it means some electrons are missing. If we got a negative charge, it means we have extra electrons. Now, one of the things that I want to stress is that you are always going to have an even number of electrons in any Lewis structure that you draw. Now, are there exceptions? Yes, there are, but you will not see them. There's a couple that come up in AP Chem, but they don't come up in Honors Chem. Very, very few exceptions. So generally speaking, you're going to see you're going to see an even number of electrons. So, for instance, if we're going to draw the Lewis structure of the ammonium ion, let's add up the number of valence electrons. You get 5 for the nitrogen, 4 for each of the hydrogens. That's 9. But the 1+ charge means 1 has been taken away, so we only have 8 valence electrons. We remove an electron because of the +1 charge. Now, we arrange it just like we did before, nitrogen in the middle, hydrogens around it. We connect it up, make sure we put it in brackets with the charge outside. Now take a look, 2, 4, 6, 8. Oh, we used all 8 valence electrons. This is a good structure. Okay. Now things can get more complicated than this, and let's take a look at something called resonance. Well, what does resonance mean? Resonance Lewis structures occur when there's more than one way to draw a structure. In other words, there's several, could be as many as 3 equivalent ways to draw a structure. They look the same, that is, each structure looks the same, but they're just oriented differently in space. So let's take a look at the carbonate ion. Now, how do we find the number of electrons? Let's add them up. 4 for the carbon, 18 for the oxygen, that puts us at 22, but there's 2 extra ones, so 24. So that should be the right one, because we're adding 2 extra ones for the extra negative charge. Now, carbon in the middle, look at the oxygens scattered around. We connect them up, knock off 6, we got 18 left. Put on our remaining pairs, that's 9 pairs. Everything looks good except there's a problem in the center, okay? The problem in the center is that we did not have 8 electrons around the carbon. Now, before we put this double bond in, we could put it here, we could put it here, we could put it here. There's 3 exactly equivalent ways. Now, I'm just gonna draw it this way at the moment. And we gotta remember, because it's an ion, we gotta put a 2- charge in brackets around it. Now, there are 2 other possible ways to draw it. We could have the double bond here, 2 singles, or we could have the double bond here and 2 singles. When you have equivalent ways to draw the same structure, what you are doing is you are actually going to have something called resonance. So if you take a look here, I have 3 equivalent structures. All right. Now, resonance is real. All of these molecules, this is a way of drawing these molecules, but resonance has a more advanced meaning, but we're probably not going to cover it in class. But if you ask me, I will talk to you